Today we're looking at lesson 1.05, Don't Break the Chain. So our objective today is given a geometric sequence. We talked about what those were last week. I can accurately write the common ratio, that's a new vocabulary term today, and a corresponding function in 2 out of 2 problems. So here's some things to think about. What tools can I use to see patterns of growth? So we've talked about a few different tools. Can you remember some of them? Let's see, there were pictures we used. We also used tables, graphs. Let's see, maybe I can write some of these down. Tables, graphs. What else? Pictures. And we also used equations, which we've been calling functions. So all of those things can be used to model patterns. And then what does geometric growth look like in different representations? Geometric growth, what are we talking about there? Okay, so here's a story. Have you ever received an email like this? Obviously, totally legit, right? Like, the number of exclamation points in the subject line is definitely how legitimate an email is. Do not delete. Awesome savings inside. Clearly not a scam. So this says, "Hi, my name is Bill Waits, founder of the new fabulous ice cream creation shop, Super Scooper Ice Cream LLC. For a limited time, you can get a super incredible, amazing, spectacular sundae absolutely free, $15 value. You just need to forward this email to 10 friends by tomorrow, and your coupon will magically appear in your inbox. Don't let this deal get away. Offer expires 24 hours from now." Super legit. Should definitely follow these instructions, right? No, not at all. Not legit. So these are called chain mail. The chain part of it meaning that you send it to someone and that person sends it to other people and those people send it to other people, and it creates a chain between the original person who sent it and all the people who eventually receive it. So usually when people see stuff like this, they just know to ignore it. We know it's not a legitimate email, but have you ever wondered how big would it get? How many people would this reach if people didn't ignore it, if they actually did forward it on? And how fast would that growth happen? So to model this, we're going to assume it takes a full day for the email to be opened, forwarded, and then received by the next person. So basically each step that happens, each forward iteration happens on a new day. So on day 0, our good friend Bill Waits sends the email to his 5 closest friends. He decides that he doesn't need to send it to 10 people because he's special, and he also doesn't have 10 friends because he writes a lot of chain emails. So on day 1, each of the 5 people that got it forwards it to 10 people, so 50 people receive it. And then on day 2, those 50 people each send it to 10 others, so now 500 people have received it. And this pattern continues on day 3 and so on. What tools do we have to model this? Well, we've talked about a bunch of tools. We know my favorite is always to start with a table. I think that's really, it shows the pattern pretty well. So let's start with a table. So we have the day over here, the number of recipients over here. We started with 5 on day 0, 50 the next day, and then 500 the following day. Do you see a pattern here? How is this changing? And then how many people would receive the email on day 7 being a full week? Well, let's see. It looks like 5 going to 50. There could be 2 options here. We're either adding 45 or we're multiplying by 10. So it could be either of those 2. Which one is applying here, 50 to 500? Are we adding 45? Does that work? Well, 50 plus 45 is 95, which is not the same as 500. However, if we tried the multiply by 10, 50 times 10 is 500. So yes, that appears to be the pattern we're doing. So let me clear all this out, all that typing or all that writing we did here. So we've decided this is multiplying by 10. This is multiplying by 10. And we're going to continue that pattern. Now that makes sense, right? Because they sent this email to 10 people each. So we're multiplying each one by 10. This one gets multiplied by 10. We get 50,000. Then another by 10 for 500,000. Another one. We get up to 5 million here. And one more multiplied by 10, we get 50 million, so many zeros. So our pattern we saw was we're multiplying by 10, and then how many people would receive the email on day 7? Well, we look down here, 50 million people would receive the email on day 7. So that spread really fast, right? We started with 5 people on day 0, and it got up to 50 million in 7 days. But hold on a second. A few days ago, we talked about a way of writing 10 times 10 times 10 times 10 times 10, right? 7 times. So 10 multiplied by itself 7 times. We had a way of writing this, right? What was the way of writing this? This was 10 to the 7th. See, we had 1, 2, 3, 4, 5, 6, 7. We multiplied by 10 7 times. That's how we write this. So does it make sense that when we have a geometric sequence like this, that's what we call this, right? This is a geometric sequence because we're multiplying at each step. When we have a geometric sequence, it's going to result in an exponential formula. That's because we're taking the same number and multiplying it many times. And our condensed way of writing one number multiplied by itself many times is an exponential function. So let's say for a second we were multiplying by 6 each time. Multiply by 6 here. 6 times 6. Well, then we would just have 6 times 6 times 6 times 6 times however many, which would be 6 to the 7 on the 7th day, or 6 to the x on an unknown day, on whatever day we want to call x. So that's how we end up with an exponential function for a geometric sequence. So if we want to write a formula for this, we're probably going to have something in that form. This number that we multiply at each step is called the common ratio. Yesterday we talked about the common difference in arithmetic sequences, and this is kind of a similar idea. The common ratio is the number that we multiply by at each step. We multiply by 10, so in this case our common ratio is 10. And when we have a geometric sequence, this common ratio makes up the base of an exponential function. So let's see how we can come up with what that function is. To write an equation for a geometric sequence, you need 2 things. This should look pretty familiar because we talked about something similar with arithmetic sequences. You need the common ratio for geometric sequences, that number that we multiply each step by, and then the value at step 0. This is very similar to the arithmetic sequence when we needed the common difference and the value at step 0. Only now for the geometric sequence, we're going to use a different formula. We're going to use this function right here, a times b to the x, and there's that exponential we were expecting. So the 2 things we need are the common ratio and the value at step 0. A is going to be the value at step 0, that's going to be the coefficient or the number out front, and then b is going to be the common ratio. We talked about why this makes sense. The common ratio, the number we multiply at each step, is going to be the number that's raised to the exponent in the exponential equation. And that's because we multiply it at each step, multiply by 10, multiply by 10, multiply by 10, and we end up with 10 to the x. However many steps there are is what we'll raise 10 to. So let's look at this example we talked about, this chain email. What is the common ratio here? Well, the common ratio is the number that we multiply at each step. So it's going to be 10. And what is the value at step 0? How do we find that? Well, let's see. Step 0 is this one, because this is our step over here on the left side. So our value at step 0 is going to be 5. And then what is the function? Well, let's see. We talked about it being f of x equals a times b to the x. And this one is our base. The common ratio is our base. And the other one, the value at step 0, is going to be our a. So our overall formula, I said, this should be function. Our overall function is 5 times 10 to the x. That is our formula, our function for this chainmail problem. So, what if everybody actually tried to cash in these free Sundays? If it costs $4 to make one of these Sundays, how much would it cost the company to actually fulfill this chainmail promise? Well, let's see. If we look back at our table here, we said 50 million people received it on the last day. So if we took that 50 million people, 50 million, and multiplied by $4 each, that would be $200 million. And you know what else? That's actually just the people that got it on the last day, on day 7. We'd have to give them to all of these people, and all of these people, and all of these people as well, all the way up. So if we add all these together, we get, looks like 55,555,555. So we'd actually get like 55,555,555 times $4. And that equals somewhere around $222 million. I didn't do that in my head. I just put it in my calculator earlier. So it would cost the company $222 million. I don't think they have that kind of money. I don't think they planned this very well. Maybe the chainmail was not the marketing strategy to go for. Okay, so we demonstrated geometric growth today. Given a geometric sequence, you can find the common ratio being the number we multiplied each step, and write a corresponding function in 2 out of 2 problems.